Hello everyone, today's question, what is the splitting pattern in the octahedral geometry? So we know that in the octahedral geometry, the ligands will be approaching along the axis. If I just consider the metal and if I consider this to be the axis, let me consider this as x-axis which is pointing towards you and away from you. Let me consider this as y-axis which is towards your right and left. And let me consider this as z-axis which is above and below with respect to you. And all the 6 ligands will be approaching along the axis. So whatever orbitals that are present along the axis, will have a greater repulsions because these orbitals are nothing but space where we can find the electron probability. And as a ligand is approaching, it is coming through its negative end or a pair of electron end. Both are electrons. There will be electron-electron repulsions, due to which the degeneracy of 5 d orbitals is lost. Whichever orbitals are facing more repulsions, they will be raised in energy, and whichever orbitals are facing lesser repulsions will be lowered in energy according to the law of conservation of energy. So supposing that if the 6 ligands are approaching along the axis, along x and y, we have dx square minus y square orbital, and along z there is a dz square orbital. So these two orbitals will have greater repulsions and they will be raised in energy. And therefore, if at all we draw the splitting pattern, we start with 5 degenerate d orbitals. The orbitals are dxy, dxz, dyz, dz square, and dx square minus y square. Once the ligands start to approach, the environment is considered to be spherically symmetric, where the orbitals, all the orbitals are raised in energy. It is just a hypothetical situation which we call it as. From this hypothetical situation, slowly the splitting will start. Orbitals which are facing the ligands will be raised in energy. So the orbitals which are facing repulsions are dz square and dx square minus y square. The orbitals which are present in between the axis dxy, dxz and dyz, they will be facing lesser repulsions and therefore they are lowered in energy. The central line, we call it as barycenter or center of gravity line. Barycenter or center of gravity line. With respect to the center of gravity line, how much energy is decreased, the same amount of energy has to be increased. So to balance the energies, we give the energy in the form of delta or dq. Suppose if I am taking in the delta, since it is energy which is decreasing, we indicate the decrease of energy with a negative charge. So here I am showing it as minus 0.4 delta. Every electron that enters into this set of orbitals, it will stabilize the system by 0.4 delta. That stabilization energy we indicate it by minus, so minus 0.4 delta. Since it is related to octahedra, we give it as delta O, minus 0.4 delta O. Or there are arbitrary units. Apart from delta O, we also have another arbitrary unit, dq. So in dq, every electron that enters into these 3 orbitals will be stabilizing the system by minus 4 dq. Well, if an electron is stabilizing the system by minus 0.4 or minus 4, then whatever electron that is entering into the higher energy orbitals will destabilize the system. When we say destabilize, we give it in the positives, and it will destabilize the system by 0.6 delta O or 6 dq. So any electron which enters into dz square or dx square minus y square will destabilize the system by 0.6 delta O or 6 dq. Well, we have three degenerate orbital set. So every time I can't say dxy, dxz, dyz, therefore we give a label to it. And this label comes from symmetry and group theory. When we go to the character tables of symmetry and group theory octahedral, then dxy, dxz and dyz, they belong to an irreducible representation T2G, where T represents the triple degeneracy, small t should be written. 2 is with respect to the presence or absence of the principal axis or the secondary axis. If secondary axis is absent, we have to consider a vertical plane. If vertical plane is present, we give 1. If it is absent, we give 2. Or if I consider the principal axis, if it is present, we give A or B. If it is, if at all it is present, we give A. If it is absent, we give B. For the secondary axis, if it is present, we give 1. If it is absent, we give 2. So in this set of orbitals, either the secondary axis is absent or the vertical plane is absent. Therefore, we assign 2. And gerade, it is with respect to the center of inversion. Every d orbital has center of inversion. Therefore, we assign G. So T2G represents triple degeneracy. 2 is with respect to unsymmetry existing between the vertical plane absence or the absence of a secondary axis. Gerade is with respect to the presence of center of inversion. For the above set, symmetry labeling is EG. Small e always indicates double degeneracy. 2 orbitals are doubly degenerate, and 2 orbitals will be having the vertical plane. So 1 should be written, but mostly 1 is omitted. We don't write E1G, we directly write EG. Otherwise, this is actually E1G. G again represents center of inversion or the parity, gerade. So any electron which is entering into EG set will destabilize the system by 0.6 delta or 6 dq. Any electron which enters into T2G set will stabilize the system by 0.4 delta O or 4 dq. Stabilization energy we assign in the minus. So minus 0.4 or minus 4 dq. This we call it as barycenter or center of gravity. So this is the splitting pattern in octahedral geometry. Thank you.